So we're going to do some further examples of integration by parts. And let's start with something like this, the square root of x times ln of x dx. This is something that we saw before. Here, what you need to possibly do is think of square root of x as x to the 1/2, and then acknowledge that this is the derivative of what? Or rather, what would be the integral of x to the 1/2? And the answer is 2/3 x to the 3/2, okay, according to our power rule. So x to the 1/2 can be acknowledged to be 2/3 x to the 3/2 derivative times ln of x. And now we can actually get our integration by parts engine going. So this will be 2/3 x to the 3/2 ln of x minus. And now we're taking the prime over to ln of x. That becomes 1 over x. So this will be 2/3 x to the 3/2 times 1 over x dx, which of course changes to 2/3 x to the 3/2 ln of x minus 2/3 x to the 1/2 dx. And this is equal to 2/3 x to the 3/2 ln of x minus 2/3 square x to the 3/2 plus c. Well, once you do several of these examples, you realize that as long as a is different from, actually, I guess you can even do this for a, as long as a is different from -1, right? Because then the antiderivative formula is not going to hold. Then this is going to be 1 over a plus 1 x to the a plus 1 ln of x minus 1 over a plus 1 squared x to the a plus 1 plus c. That's a very general formula that you can have with this, which of course can be proven in exactly the same way without much more difficulty, actually. Let's go to a different example. Let's jazz up a little the one that we had done before, the one where we needed two integrations by parts. So we will have something like, let's do sine of 3x dx. Let's do this one. Again, you can pause your video. This will require two integrations by parts, after which you will come back to the same expression, and then you can solve for it, and that will give you your integral. Let's write this a little better, so that it looks a little better. So sine. Okay, so in the example that we did in the first video for integration by parts, we start by acknowledging that the cosine component as the derivative of something. I said back then that it could have been e to the x. Let's work with e to the 2x. The one thing that you have to be careful with is that for the two integrations by parts that you're going to do, it will have to be the same thing that you choose. So if we choose e to the 2x in the first integration by parts, it should be also e to the 2x in the second integration by parts. If you decide to go with a trigonometric as the thing that you're going to integrate partially, then you should do the same thing in the second integration by parts. So here we're acknowledging that e to the 2x is the derivative of e to the 2x over 2. So we get our integration by parts engine started, and this will be e to the 2x over 2 sine of 3x. And now take the derivative immediately onto sine of 3x. What is the derivative of sine of 3x? Let's think. Chain rule. Think of 3x as y. We have sine of y. The derivative of sine of y is cosine of y, and you need to multiply by the derivative of what you designate as y, which is 3x. The derivative of 3x is 3. So you will get e to the 2x over 2 cosine of 3x times 3 dx. This is the case where you need to do a little bit of cleanup. I mean, okay, so here's how I'm trying to write the first part a little better. As for the second part, I have a 3 to extract and a 2, 1 over 2 if you like. So minus 3 over 2 e to the 2x cosine of 3x dx. And here comes the second integration by parts. I have to acknowledge e to the 2x as the derivative of e to the x over 2. Like I said, if I want to be consistent, what would happen if you went with cosine of 3x and said cosine of 3x is the derivative of sine of 3x over 3? Then you would go back to the very beginning. And when I say to the very beginning, not an expression that contains the integral that you had in the very beginning, but I mean e to the 2 sine x, e to the 2x sine of 3x dx, just like that. And you would have been at square 0 again. So this is 1/2 e to the 2x sine of 3x minus 3/2, and now we acknowledge that this is e to the 2x over 2 derivative cosine of 3x dx, which is 1/2 e to the 2x sine of 3x minus 3/2. And now we perform the integration in here. So we have e to the 2x over 2 times cosine of 3x minus integral. And now we put the prime on the other. And what is the on the other component, on cosine of 3x, meaning we take the derivative of cosine of 3x. What is the derivative of cosine of 3x? It's negative sine of 3x times 3. That's the derivative. And now we need to do a lot of cleanup. So let's see. 1/2 e to the 2x sine of 3x. And here we will have minus 3/4 e to the 2x cosine of 3x. And now we have how many minuses? We have 3 minuses. So this will be minus, and we can extract the 3. So this will be 9 over 4 because we're extracting the 3/2 from the integral, and we already have the 3/2 here. And this will be e to the 2x sine of 3x dx. And this is what we were trying to get, meaning we try to get pretty much the same thing that we start up with. And now we have to acknowledge that this is equal to that. Let's write it as one equation so that we can all see it. So we have e to the 2x sine of 3x dx. So we can write from this it follows, and this is, we can clear denominators here. So we can have 2e to the 2x sine of 3x minus 3 e to the 2x cosine of 3x over 4 minus 9/4 e to the 2x sine of 3x dx. So at this point, we bring this term over to the other side. So we have 1 plus 9/4. How much is 1 plus 9/4? It's 13 over 4. So we will have 13 over 4 times e to the 2x sine of 3x dx is equal to 2e to the 2x sine of 3x minus 3 e to the 2x cosine of 3x over 4 plus c. And eventually we divide by 13 over 4, and this gives us e to the 2x sine of 3x dx is equal to 2e to the 2x sine of 3x minus 3e to the 2x cosine of 3x over 13. Why 13? You have over 4, and now you divide by 13 over 4. the denominators by 4 cancel pretty much each other. You can also think of dividing by 13/4 as multiplying by 4/13. The 4's cancel and you get 13 on the denominator plus c. And that's the final answer. Okay, a wonderful problem. Let's also do a problem where we will mix up integration by parts and substitution. And it's something like this. This is a very interesting problem. It's one of those problems that I suspect that unless you have seen it before, that it's you can find the antiderivative. In fact, usually I like to do the following. I like to ask, out of these two integrals, which one do you think is doable? And you know, most people go with cosine of x squared. So if I told you that one is doable, and when I say doable, I mean that the antiderivative can be expressed using functions that we already know. So here, most people actually go with cosine of x squared, thinking that x squared is much simpler to handle than square root of x. But no, it turns out that the one that is doable is cosine of square root of x, whereas cosine of x squared is not doable using functions that we have already defined. So let's do it. So how do you do it? This has an interesting substitution. It's the principle that pretty much any substitution can be done. So you're using the substitution u is equal to square root of x. At first, you might think that, well, where is the derivative of square root of x, which is 1/2 square root of x? And you're right, it's nowhere to be found. But let's see what happens. 1/2 square root of x dx, and now you multiply both sides by 2 square root of x, and this is where you should allow this only temporarily to have the two variables on the same side, but you know that u is equal to square root of x, so this becomes 2u du is equal to dx, and eventually this becomes what? Cosine of u, and your dx is 2u du. And now the 2 comes outside. Let's write this as u cosine u, and this is where you finally use integration by parts, which, by the way, if you were doing the UV thing, what would you do here? It would be a little bit of a problem, right? But we're not doing the UV thing, so we're not really concerned about that, because here, all we need to do is acknowledge that cosine is the derivative of sine. And since we have a 2, we want to put a parenthesis and do the whole thing inside that parenthesis. So, and we need to take the derivative of u, which is 1, clean it up a little, and this will give you 2u sine of u minus 2 sine u du. And what is an antiderivative for sine? It's negative cosine, and 2 negatives will give you a positive, so it's 2u sine u plus 2 cosine u plus c. And don't forget to go back to your original variable, right? So this is 2 square root of x sine of square root of x plus 2 cosine of square root of x plus c. Okay, and that's the antiderivative for cosine of square root of x. It's absolutely doable, and this brings us to the end of our second lecture on integration by parts. We will have one more lecture where we're going to do some combined examples that are largely based on integration by parts, but they could be considered as examples of more further examples of integration that now combine pretty much everything. And we're going to show some new ideas. Thanks for watching.